Welcome to the Explainer. Okay, get ready, because today we're diving straight into a seriously fascinating corner of optical physics. We're literally going to transform the way you see the world. If you've ever looked in a funhouse mirror and wondered how it magically stretches or shrinks your face, well, you're in exactly the right place. We're building a practical masterclass right here, mastering the art of ray diagrams and decoding the everyday secrets of light.
But hey, before we start drawing lines and mapping out light rays, I want you to think about a quick real-world puzzle. Have you ever noticed that an ambulance has the word ambulance printed completely backward on its hood? I mean, it looks like absolute nonsense when you're just standing on the sidewalk looking directly at it, right? Why on earth would they do that? Keep that question in the back of your mind, because how light and mirrors play tricks on our eyes is exactly what we're unraveling today.
All right, let's quickly hit our syllabus. We'll start with the nature of light, break down the anatomy of spherical mirrors, learn the rules for ray diagrams, walk through a step-by-step drawing guide, and then bring it all home with real-world optics.
Section 1. The nature of light. Let's start with a super basic, foundational question. What exactly are we dealing with when we talk about light? So, the true nature of light is actually kind of wild. If an obstacle in the path of light is incredibly tiny, light actually bends around it. It completely refuses to walk in a straight line, acting way more like a wave. That's a whole thing called diffraction. And honestly, at the quantum level, it even behaves like a stream of particles. But here's our secret weapon for this masterclass. For everyday, macroscopic optics, like the mirrors and lenses we're dealing with, we don't need to worry about the quantum stuff. We just use a much simpler model. We simply treat light as a straight-line ray.
Like our source material points out, light seems to travel along straight-line paths in a transparent medium. Treating light as a perfectly straight line, a ray, is basically the ultimate cheat code for optics. It lets us use simple, straightforward geometry to predict exactly where a reflection's going to go and what an image will end up looking like.
Moving on to Section 2, the anatomy of spherical mirrors. Now that we know we're drawing straight lines, we really need to get a handle on our toolkit and the vocabulary of the surfaces we're bouncing that light off of.
Imagine just taking a big, hollow glass sphere and slicing a piece right out of it. If the reflecting surface curves inward, facing the center of that imaginary sphere, kind of like the bowl of a soup spoon, that's your concave mirror. But if the reflecting surface bulges outward, boom, that's a convex mirror. Now, before we actually map a mirror, we really got to clear up a massive misconception about the laws of reflection. The law states that the incident ray coming in, the reflected ray bouncing off, and the normal, perpendicular line all lie in the same plane. But listen closely, this plane is not the physical surface of the mirror itself. Actually, scratch that, it's more like an invisible, imaginary 2D vertical slice of space where these three lines perfectly align. Imagine a flat sheet of paper standing straight up on the mirror. That right there is the plane we're talking about.
Okay, to draw our diagrams, we need some map coordinates. The dead center of the mirror's physical surface is the pole, marked P. The center of that giant imaginary sphere the mirror was cut from, that's the center of curvature, or C. Plop exactly halfway between P and C, and you've got the principal focus, or F. And the distance from the pole to the center of curvature is simply the radius. Since F is perfectly in the middle, the radius is always exactly twice the focal length. So R equals 2F. Easy enough, right?
Section 3. Rules for ray diagrams. We've got our map, we've got our vocabulary, now we're going to learn the undeniable traffic laws of light rays.
And you know what's really cool? Notice how beautifully simple these geometric rules are to memorize for a concave mirror. Law 1, a ray coming in parallel to the principal axis will absolutely always reflect through the focus. Law 2 is the exact reverse. A ray passing through the focus will reflect out parallel. Law 3, a ray passing through the center of curvature hits the mirror dead on and bounces right back along that exact same path. And finally, Law 4, a ray striking the pole reflects at the exact same angle it came in at.
Now you might be sitting there thinking, wait, a real object emits literally millions of light rays. How on earth am I supposed to draw that? Well, here is the sheer magic of ray diagrams. You don't need a million rays. To locate an image and figure out exactly what it looks like, you only need to pick 2 of those traffic laws. That's it. Just 2 perfectly placed intersecting lines are totally enough to map out reality.
Which brings us to Section 4, our step-by-step drawing guide. All right, it's time to put pencil to paper. Let's walk through the actual execution of drawing one of these ray diagrams.
Let's pretend we're at a whiteboard mapping this out together. Step 1, just draw a straight horizontal line. That's your principal axis, and mark your pole, focus, and center of curvature. Step 2, plop your object down.
Usually we just draw an upright arrow resting on that axis. Step 3, from the very top tip of that arrow, draw 2 rays using the traffic laws we just nailed down. Like maybe one parallel ray that bounces through the focus, and one ray through the focus that bounces parallel. Step 4, find exactly where those 2 reflected rays cross paths. That little intersection point, that is exactly where the top of your image is going to form.
Let's actually apply those steps and see what happens. Notice how the object, the arrow way over on the left, is placed far away, well beyond the center of curvature, C. By drawing just one parallel ray and one focal ray, we easily find our intersection point. But look at where it formed. It created an image right smack between C and F, and notice that the new image arrow is pointing downward and is physically way smaller than the original object.
So this whole process actually builds into a highly predictable pattern. Depending on exactly where you place that original object, the resulting image changes in a totally mathematical way. Like if you slide the object exactly onto C, the image forms exactly at C as well. But it's the exact same size and totally upside down. If you move the object closer, the image moves further away and gets bigger. It really is a perfect geometric dance. Now, as we map these out, we constantly run into 2 completely distinct types of images. A real image happens when light rays actually physically cross paths in front of the mirror, just like the diagram we were just looking at. And because they physically meet, they project upside down or inverted. But sometimes the rays bounce off and just spread apart. When they diverge, they are literally never going to meet in the real world. So our brains have to trace those rays backward, behind the mirror, to find where they appear to meet. This creates a virtual image, which magically always appears right side up or erect. So, the absolutely crucial takeaway here is that these properties are a package deal. You will never, ever see a real, upright image in these basic spherical mirror diagrams. No way. If it's real, it's inverted. If it's virtual, it's erect. Commit that to memory, and you'll always know for sure if your diagram is spot on.
And finally, Section 5, Real-World Optical Applications. Let's step away from the whiteboard and the textbook geometry for a second. Let's look at the fascinating ways we actually use these exact geometric illusions out in the messy, everyday real world.
All right, time to answer our opening hook. Why is ambulance printed backward? Well, it's due to this quirky phenomenon called lateral inversion. When you look in a standard flat plane mirror, your image is virtual and erect, but the left and right sides are entirely swapped. So, by printing ambulance laterally inverted on the hood of the rig, a driver looking in their flat rearview mirror sees the letters perfectly flip back to normal. It lets them instantly read the word and get the heck out of the way. Pretty clever, right?
But what about our curved mirrors? Well, concave mirrors are absolute converging powerhouses. If you put an object really close to a concave mirror, like right between the pole and the focus, it creates a massive, magnified, virtual, and erect image. This is exactly why dentists use those tiny concave mirrors to get a huge upright view of your teeth, and it's why your magnifying shaving mirror makes your face look so big. On a much larger scale, concave mirrors can take parallel rays from the sun and converge them all into one single intensely hot focal point to literally power solar furnaces.
Convex mirrors, on the other hand, bulge outwards. They are the diverging spreaders of light. No matter where you put an object in front of a convex mirror, it's always going to give you a virtual, erect, and diminished, or shrunken, image. Now, why is that useful? Well, because it shrinks everything down, it captures a massive field of view. This is exactly why convex mirrors are used as the side view mirrors on your car. They uniquely give drivers a smaller, upright view of a huge area of traffic behind them, something a flat mirror could never pull off.
So we've built a pretty incredible toolkit today. By simply pretending light travels in perfectly straight lines, we can mathematically map out images, build giant solar furnaces, design precise dental tools, and engineer everyday traffic safety. But hey, remember our very first slide? Light isn't just a straight line. It's a wave that bends and a particle that bounces. So I really want to leave you with this thought. If mastering just the simple, macroscopic straight-line illusion allows us to manipulate the world this much, what profound, universe-altering secrets are hiding in the true quantum, wave, and particle nature of light that we haven't even begun to explore? Thank you so much for joining this explainer. Keep asking questions, and I'll catch you next time.